Good evening. Good evening, Sharath and all. Hello, good evening.
Good evening.
Good, Angel, madam has joined. Hello, Angel.
Yes, ma'am.
Madam has joined, Angel.
Yes, ma'am. She has joined.
Uh, Hello. Good evening, Dr. Jisha.
Good
Good evening.
evening.
Good evening, madam. I am Lisha Paul, heads of chair.
Oh, hello, ma'am.
Uh,
Good evening, everyone. I trust you are all doing well and ready for an engaging session. I'm delighted to extend a warm welcome to every one of you on behalf of the IEEE Education Society Kerala section to the third episode of our talk series, ProTalks, where seasoned professionals provide insightful talks about their respective fields. We have the privilege of hosting a session on a walk through robotic technologies by Dr. Jisha V R, Dean, UG Studies and Professor, Department of Electrical Engineering, College of Engineering, Trivandrum. The depth of knowledge possessed by Dr. Jisha in robotic technologies is truly impressive. Her expertise spans across various facets of robotics, showcasing a profound understanding of both theoretical concepts and practical applications. With a keen eye for detail and a knack for innovation, they have consistently demonstrated an ability to tackle complex challenges in the field. We will delve into the realm of robotics technologies, exploring its fundamental principles and remarkable milestones achieved thus far. Additionally, she will enlighten us on the plethora of exciting career prospects with this dynamic field, leveraging her extensive experience and expertise. To commence our session, I would like to invite Professor Reshna S., STEM and Hack Coordinator, Education Society, Kerala section, to deliver the welcoming address. Ma'am, please. Ma'am, Reshna, ma'am.
രശ്മി മാഡം ജോയിൻ ചെയ്തിട്ടില്ലേ? Hello, Angel.
Jisha madam, shall I introduce? I am Bindu here.
Yeah, Bindu, you can invite.
Hello.
Hello. Bindu madam, you can invite Bindu madam. Yes, you are audible, Bindu madam.
Yeah. Is my audio clear?
Yes.
You are audible. You are audible.
Without any delay, we can start. Dr. Jisha V R was a colleague of mine and a very good friend of mine. She is Dean UG Studies in the reputed College of Engineering, Trivandrum, and also professor in the Department of Electrical Engineering, and a very good teacher. Which is will be proved by all this, which has been proved by students of hers all through her years. And she's an expert in robotic technologies. And she was I feel that she was a chairperson of the Robotic Society of IEEE. And she is a pioneer in that field in our College of Engineering, Trivandrum. She was instrumental in setting up the Robotic Society chapter in CET. And all over Kerala, many talks have been done by her in this field. And also, she is very passionate about it. That is what I have understood. She's a friend of mine. So I'm very happy to introduce her to you, and I'm very sure that all the audience, all those are in the audience, will benefit out of it. And every student of hers will always say that she is the best teacher, one of the best teachers that they had, and she is the inspiration behind why they have chosen robotics. Even startups have been many of these startups have been initiated by some of our students in robotic technologies. With great pleasure, and I feel privileged to welcome you, Dr. Jisha, for this talk.
Thank you so much. So happy to hear from my former colleague, Dr. Bindu V R. Thank you so much for the invitation. Thank you so much, ETSO Kerala chapter, for this opportunity. So this talk is so special to me because this is my 50th technical talk outside CET. So in this way, so it's my colleague who has invited me for this landmark technical talk, I should say. I really consider this as a privilege to interact with the budding engineers of Kerala. Okay, so thank you, and let's move on. I hope my screen is visible.
Yes.
Okay. So the title which I thought of sharing with you, the topic which I thought of sharing with you is a walkthrough robotic technologies. Like I won't be able to go much deeper into the concepts of robotics. I'll just take you to the world of robotics so that someone among you wishes to pursue studies in robotics or take up projects in robotics. I hope this will definitely be helpful for you. Okay, so let's start with the definition of robotics. Okay, so what is basically robotics? So it is we can call it as it's a technology of designing and building robots suitable for real life applications. And in automated manufacturing and other environments. In automated manufacturing, because majority of the robots which are seen worldwide, like if you consider the robotic population worldwide, the number of robots, the number of robots employed in automated manufacturing industry are more compared to any other domain. Okay, so that is why specifically it is written as automated manufacturing. So what is basically a robot? So generally, maybe when we are in school, when we are maybe beginners in robotics, what comes to our mind, like when we hear the word robot. So is it a machine which looks like a human being? Maybe in my school days, like when I hear the word robot, this is something which comes to my mind. Okay, so it's only a humanoid robot like that. So this is basically only one class of robot. So if you can see two different configuration. One is a very famous humanoid configuration by Honda, which is known as Asimo. So is this the only one robot which is available or existing in the world? No. So this is another class which is called robotic arms or robotic manipulators. So if you look at this now, this is like a human arm, like our arm, wherein the one end is fixed. So if you look at these two manipulators, we call this as manipulator. One end is fixed. See, this also fixed, and it has multiple links, and there is a gripper here. Okay, so we call this configuration, like our arm-like configuration, as a robotic manipulator. So this is another class. Okay, and any other class of robots available? Yes. So these are actually wheeled mobile robots. So so if you look at this slide, there are many robotic configurations you could see. These are very simple configurations, but this one can be employed in outdoor environments also, because the wheels look little big. And this one, if you look at, this is a very famous robot, Pathfinder robot with multiple wheels which can move even in uneven terrain. So this is another class of robots which is called mobile robots, but it's specifically wheeled mobile robot, because the first configuration which I have shown is basically, it's also a mobile robot, but it is a legged configuration, right? So this is another class, and this is another one. This is also another class of mobile robots, because moving robots with more number of legs. So if you look at this, this is a famous Boston Dynamics dog-like robot, which is a 4-legged robot. So this is a hexapod. So these are all different classes of robots. And then comes aerial robots, which are flying robots. Okay, so this is basically one configuration, very famous configuration, which is called a quadcopter, because there are 4 rotors. So that's why it's called quadcopter. And this is another simple configuration, but no control perspective, the helicopter-like configuration. But this control from control perspective, this is little difficult to control than this quadcopter-like robot. Okay. And this is the last class which I have, or last group of robots which I have included in the presentation, wherein these are the robots which are moving in water. So if you look at this, this is actually a pond cleaning robot which is moving over the surface of water, but this can go deep inside and do some analysis or maybe monitoring water pollution. So what I wanted to convey is that robot means it's not all the robots are human-like. There can be configurations like these. There can be many more configurations as well. So I have not included all the robotic configurations. Okay. So what is basically a robot? So it is, in simple means, we can say that it is an electromechanical machine. Okay, so it has a mechanical structure, and we will write some program or electronic, or there will be some electronic circuitry which is used for controlling this robot. So this robot can be semi-autonomous or it can be autonomous also. So this is decided by, so if we are using only electronic circuitry, means it will be like semi-autonomous or something, but using computer programs, we can make this as fully autonomous robot. So basically, from where this word robot has come, it has come from the word robota, which means, it's a Czech word which means forced laborer. So if you look at the robotic population worldwide, they are all used as laborers, and population wise, more like, what do you think? Can anyone say? See, I have shown different robotic configurations, right? So starting from humanoid, then I have shown the manipulator, then I have shown mobile robot, wheeled mobile robot, legged configurations, and the robots which are moving in water. Okay, so among this, population wise, which one is dominating? Can anyone say?
Manipulators.
Yes, manipulators, right answer. Because if you look at percentage wise, almost 90% of the robot worldwide are manipulators, which are used for automation purposes. So if you go to some car manufacturing industry or chemical processing industry, so everywhere, these robots are used for different pick and place application in general. Okay. And I have seen many students designing robotic manipulators, because robotic manipulators, research perspective, the mechanical design of robotic manipulators is kind of saturated, I should say. But like many students are working with these kinds of robotic configurations. Let's suppose, like the general trend, what I've seen is that BTech students, what they are doing is, okay, they will try to build a robotic arm with whatever C bracket or L brackets which are available to them, or the motors which they have, or which can be easily purchased. Okay, the gripper which is readily available for purchase, and with all those things, no, they'll assemble and build a robot. Okay, I am not discouraging anyone. Okay, but no, like whenever we are building a robot, no, it should be used for a task. Okay, so it should be used for a pick and place task. Okay, so for example, suppose I am using this robot for picking and placing this bottle. Okay, so suppose if this is to be done in such a way that the robot has to start from this point. Okay, the point A, the robot has to the bottle may be kept at this point A, and the bottle should be kept at point B. Okay, so let this be point B. Okay, can this robot do that? That's the question. Okay, so what generally the students are doing, okay, with the available components, they'll assemble everything, and they'll try to keep the bottle somewhere here and try to pick that, and that will not work. Okay, and then what they'll do is they'll place the bottle here, and then no, they'll try to pick. Yes, it works. Okay, then maybe like I'm marking that point as C. Okay, from C, this robot will be able to pick the bottle, and suppose at D the robot is able to this robot can place the bottle. So what this robot does is, no, it takes the bottle from point C and keeps at point D. But is that what we want? Because no, engineers are supposed to do the tasks which are assigned to us, right? So the task assigned to me is pick the bottle from A and place it at B. So can I design a robot in such a way that the robot must pick the bottle from point A and place at B? So, without knowing some basic robotic concepts, no, you won't be able to do that. Okay, so for that, no, understanding some concepts are needed in order to achieve this task. Okay, so how we can do that? So for that, no, some basic concepts we'll see. And see how about this? No, this is another example where see the robot is moving through a path. See the end effector. We call the last part of this robotic manipulator as end effector. This has to move through a path. Okay, can I do that? Okay, that's another question. And suppose this example, can I do this? See, specifically from this point, this is to be picked, and it should be placed at this point. So whenever we are designing a robot, suppose if it's a robotic manipulator, no, it should satisfy the requirement. Okay, it should not be in such a way that it should not be like that. No, like from where that point A, B, C, D, wherever I wish to keep the object, I should be able to do that. Okay. So your robot should be able to do that. So another example, no, this is a line follower. Okay, many might have seen that. Many might have built line follower robots also. So what generally people do is, no, like there'll be a line which is marked on the floor, and then the robot will be designed to follow this line. But I am telling you, see, I'm imagining as a line which is on the floor in the room where I'm sitting. Okay, it's just imagination. There is no line over there. Will I be able to move the robot through that straight line? And suppose I'm thinking of moving the robot through a circle. Okay, so somewhat like this. Will I be able to do that without drawing a circle? Okay, so you should be able to do that. So see, so some of my BTech students have done this project, no, so many years back, wherein see where the robot is moving, it's moving through a circle. If you look at this, this robot is moving through a circle, and there is no circle drawn. Okay, so how this is achieved? Okay, so if you know a little bit of math, you will be able to achieve this task. Okay, So, and another common task which is taken up by UG students is obstacle avoidance robot. Okay, so what they'll do is they will generally use a sonar sensor, or initially they start with IR sensor, or they may integrate a sonar sensor or laser rangefinder. So, what they do is see what obstacle avoidance, how they are doing. Like, suppose the robot is moving forward like this, and when an obstacle is encountered, what the robot does is, okay, take a right turn or take a left turn. So that will be their algorithm. Okay. So is that what the robot is supposed to do? No, right? Because no, this robot will be assigned to do some task. Okay, maybe the robot has to move from point A to B. While moving from A to B, it encounters an obstacle, and then now it has to overcome this obstacle and reach B. Okay, so can this be done? Okay, that should be in our mind, rather than no, like when the robot is like when the obstacle avoidance robot is built, no, just take a left turn or take a right turn, where it will go. Are you people thinking of the destination point also? So whenever we are thinking of building an obstacle avoidance robot, we should think of this as well, this aspect as well, or something like this. See, so if you look at this, no, this is a start point in a scenario, and this is a goal point, and you could see there are some obstacles, but no, like this robot is avoiding all the obstacles and reaching the destination. So you should think of whenever you are building a robot or obstacle avoidance robot, you should also think in this way. And the next level is, these all these obstacles are static obstacles. Suppose if the obstacle is moving, then how to avoid that and move forward. Okay, so all these things should be in your mind whenever you are working with robotic projects. So can we claim robotics as it belongs to only one particular engineering discipline? No, right? So it's an interdisciplinary area where anyone will be able to contribute, whether you belong to a mechanical stream, electrical stream, electronics engineering, or computer science. So you all will be able to contribute if you wish to work in robotics. Now, suppose I am basically from electrical background. So what generally I'll do is, the mechanical design part, I will not be much interested in, or I will not be aware of that. And once the robot is available, I know how to control that to move from one particular point to other, or how it can be moved through a particular trajectory. Like that, I'll be able to know. I will be able to do. And being an electronics engineer, what you will be able to do is, you will be able to add more sensors. Sensor integration can be done, or sensor fusion can be done, like image processing also. Suppose if you are using a camera as a sensor, those data can be manipulated, the obstacle avoidance can be done. So all those things, an electronics engineer will be able to contribute. And a computer science engineer, like whenever we are coming with an algorithm, he or she will be able to design optimal a program for controlling or achieving all these tasks. So so that is generally like anyone in this group will be able to contribute. And as I was mentioning earlier, like most of the robots worldwide are industrial robots, and they have achieved its greatest success to date in the world of industrial manufacturing. And see, this is the evolution of robots now, starting with if you look at 60s and 70s. So initially it's the industrial robots, and then later different other robots like mobile robots, like walking, humanoid, all these robots have come. And nowadays it's a era of, I should say, service robots. Now itself, I think many among you will be having home cleaning robots. Now maybe in coming years we could see robots which are able to help elderly people, or maybe as a tuition teacher for kids. So those kinds of robots are yet to come. So mainly in service robots, we'll be able to see more revolutions in upcoming years. And I'll just give you some brief about the manipulators, like what are its parts and some basic math, so that if you are interested in working deep in these manipulator robots, you will be able to do that. Okay, so if you consider a manipulator or robot arm, if you consider a manipulator or robot arm, it is very much similar to human upper limbs. And so basically a manipulator or robot arm is generally defined as an open kinematic chain of rigid links interconnected by movable joints. That means it is open to move. Okay, only one end is fixed, then the other end is moving. Okay, so that we call as the open kinematic chain. But no, if this is fixed and this is fixed, see, these two ends are fixed and in between part is moving, then we call it as a closed kinematic chain. Okay, so that's the basic concept of open and closed kinematic chain. So this is another configuration which we call as a closed kinematic chain, very famous toward platform, which is basically used for like simulating space-like environments. So this platform is generally used. So just a classification of a closed and open kinematic chain, and some terminologies also I will mention. Because if you consider a manipulator, it has links, joints, and other structural elements. And end effector means it is the part which is connected to the last, which is the last part of or the last link of any manipulator, I should say. And actuators means which is causing the robot to move. Okay, so we call them as muscles of manipulators. So muscles can be servomotor. So that means, see how beautifully we are moving our hand, right? But how, like, suppose when we think of replacing this with motor, we'll understand how difficult it is. Okay, so we can use servo motors, stepper motors, and in some cases, we go for hydraulic or pneumatic actuators. Because in car manufacturing industry, the payload to be manipulated is a car. So car means, you can imagine what is the weight of a car. So a ordinary servo motor or stepper motor will not be able to manipulate that payload, and only hydraulic actuators will be able to manage that. And in some scenarios, like where in food processing industry or something like that, there we can't employ hydraulic actuators because there can be oil leakage. So in those scenarios, we go for pneumatic actuators, which are air actuated actuators, but this is oil actuated actuators, which are referred to as hydraulic actuators. And then always if you wish to make a robot autonomous, definitely sensors are to be integrated, like encoders, camera, touch sensors, sonar sensors, IR sensors, light sensors. It depends on the application which you are going to work with. And finally, most importantly, there should be a controller which controls all the motion. So when you integrate all these, you will get a manipulator. But when you think of a mobile robot, it can be legged or wheeled robot. All these things are common. So there will not be any manipulator or end effector. All other parts will be there. There will be a chassis. Okay. And of course, there will be actuators. It may not be servo or stepper motor. It will be direct DC motors or something like that. And because continuously rotating. See, in a manipulator, it's just theta control. Okay, just angle control. Theta 1, we say theta 2, theta 3, like that. But in a mobile robot, we say the velocity of the motor is to be controlled. And then a mobile robot will also have sensors control. So sensors, controller, and the actuators are common in all the robots which we work with. And in a manipulator, so as I was mentioning, there are links and joints. So the joint is connecting two links, and there are two types of joints. One is called revolute joint, another is called prismatic joint. Revolute means all our joints in the body are revolute joints. Prismatic, in some applications, we may need robots But no, for us, all the joints are revolute joints only. And these are some terminologies. This also I will just go through the standard terminologies if you wish to work with robots. So the first one is a work envelope. Work envelope means no, it is a locus of points in 3D space where the end effector can reach. Because no, this is very important. Okay. See, the robot is going to do pick and place. Okay. So is it going to work inside a rectangular box? Or is it going to work inside a cylindrical envelope? Or is it going to work inside a spherical envelope? You should have an idea, because no, suppose there are parts which are moving in a conveyor and the robot has to pick and place at some point. Then no, the where the arm is moving, you should have an idea. Okay, what should be the work envelope? Should it be a sphere? Then what should be the robotic configuration? Okay, that is how you decide. Based on the application which you are working with, you need to choose that particular robotic configuration. Okay. And how the work envelope looks like, that is decided by the first 3 joints or major axis of the robot, and the remaining joints are called minor axis of the robot. And like how the work envelope looks like is decided by the major axis. Okay. And see, these are the common configurations. See, this is what I was mentioning. See, this is a rectangular box like work envelope. So that means the robot will be working inside. The end effector will be able to move within that rectangular box. See, this is a cylindrical configuration wherein the robot end effector will be able to move within the cylindrical envelope. And this is called spherical, and this is called articulated. So that means, see, suppose if you want a box-like configuration, we will go for this robotic configuration, which is called prismatic configuration. PPP we call. Okay. So next one is cylindrical configuration, which is called R. It is revolute prismatic, which yields a cylindrical work envelope. And next is spherical, which is RR, revolute prismatic. And the last one is articulated, means RRR. Okay. So suppose you are asked to automate a process. Maybe in this era, you don't have to design a robot for that particular task. What you may have to do is, okay, which configuration I should opt for? In this particular, for automating this industry, which configuration I should opt for? So that we may have to choose. So because these are all standard configurations, and from that, no, you will be able to choose which one is suitable for your application. And this is also another famous concept in robotics, which is called degrees of freedom, which means that the number of independent movements that can be performed. Because for example, if the degrees of freedom of a robot is less, means like suppose you have a pen, okay, pen like this, and suppose the robot has to place the pen at this point, okay, the position is okay. But no, sometimes I may have to hold the pen like this, like that. So this is orientation is different. Okay. So if the robot has more degrees of freedom, means more joints, then no, you will be able to position the robot at orient the end effector at any position and orientation. Okay. And if the degrees of freedom is more, then no, we say the robot is more dexterous, or we say that the dexterity is more. That means no, like suppose an object is kept inside a box, okay, and in ordinary way, no, that will be kept on the table. Then no, it can pick and place like that. But no, if it is kept inside a box, no, it has to overcome the obstacle, go inside and pick. No, if it is having more degrees of freedom, more joints, no, it will be easily able to pick that. Okay. So that is called degrees of freedom. And see, if you look at this, no, there are, see our hand. how God has blessed us with these many degrees of freedom. So that is why we are able to do so many things. We are able to see the dancers, see what all things they are doing. So suppose if you think of designing an arm which is capable of doing the typical Bharatanatyam mudras and all, no, this is going to be really very challenging. Okay, so we are blessed with these many degrees of freedom, so many degrees of freedom human arm is having. And like when you are designing robot from scratch, no, you have to know some mathematics called like coordinate transformations, because no, coordinate transformation means like see, suppose if you wish to specify the position and orientation of the end effector, the speciality of an arm is that, no, see, when this joint is moving, this arm is moving, this link is moving, this also is moving. So simultaneously, when these two are moving, what happens? How to find the end effector position? Okay. So for that, what we do is we make use of what is called coordinate transformation. And so what we do generally do is we will just assign frames at one frame, fixed frame here, one frame of reference here, one frame of reference here. And first what I'll do is I'll just find the position of this movable frame with respect to this, then this movable frame with respect to this, and this movable frame with respect to this, and I'll find the transformation, and then I'll find the product, so that no, I will be able to find what is the end effector position, with respect to the base. So this helps in finding that. Okay, if you wish to design a manipulator, then this will be of use for you. Otherwise, no, you can just choose a configuration and work with that. And two more terminologies I will explain, and one is called kinematics. This is called robot arm kinematics. So this means it is a study of motion without considering forces and moments. Okay, so for example, suppose if the arm is to be simply moved without taking a payload, then no, this kinematics is going to help us. Okay, but no, suppose if the robot is taking some 10 kg payload, so then this study will not help. So then I have to go for dynamics. Dynamics means it is the motion considering, it's the study of motion considering forces and moments. So this kinematics means without considering forces and moments, and dynamics means considering forces and moments. So in kinematics, actually, there are two terminologies. One is called direct kinematics and another is called inverse kinematics. See, direct or forward kinematics means if you know the joint angles, how to find the end effector position. So that is called for, if you know theta 1, theta 2, theta 3, what is the end effector position? Inverse kinematics means you know the end effector position, find what is theta 1, theta 2, theta 3. Okay, so that is called inverse kinematics. So this is really needed when you wish to move the arm through a particular path. Okay, this path, the end effector has to move. So if this is the point, what should be theta 1, theta 2, theta 3? If this point, what is theta 1, theta 2, theta 3? So you need to control this in such a way that at each point, this inverse kinematics is to be solved. Then only you will be able to do that. Okay. And there are some terminologies. I'm not going to the details of that. So this is actually a typical illustration of frame assignment in a robot and finding the end effector position. And see, this is what I was explaining, which is called robot dynamics bearing. Okay, so if the robot movement is to be studied considering forces and moments, then we work with robot dynamics. So this I will explain once again with respect to a mobile robot. Okay, for example, suppose you are asked to design a robot in a hospital or in office. Okay, initially to work with you, the robot has to move from one room to another, and the payload which is taken by the robot is very less, okay, less than 1 kg. Just imagine. So in that case, you can work with kinematic based analysis, okay. But no, suppose if you are designing a robot which is moving from one room to other taking 10 kg payload or 50 kg payload, so in that case, no, like for analyzing, you can't work, or designing a controller, you have to do the dynamic analysis, or that means you need to consider the model which which takes into account forces and moments. Otherwise, no, you will not be able to move the robot to a desired position. The robot will not. For example, once again, that if you are not clear with that, no, once again I can. In the first case, okay, in the first case, if the robot is controlled by kinematics based, so the payload will be very less, okay, maybe 1 kg or less. So in that case, no, what you have to give as control to the robot are the left wheel and right wheel velocities. Okay, but no, in dynamics, suppose if you it's actually it is based on, see, some customer will come and ask you, okay, design me a robot which can take 50 kg payload. Okay, so suppose he is asking you to design a robot which can take 50 kg, then no, what you have to do is not it should not be the velocity control. You need to design a controller such that the robot should be able to the controller should be able to find what is the right wheel torque and left wheel torque. Okay, so for this, no, you have to take the dynamic model where the forces and moments will be taken or coming in picture, but here no, only position and velocities will be coming. Okay, position and velocity. Okay, so that means no, like exactly you will be able to control the robot in these two scenarios. So that is the importance of knowing kinematics and dynamics. Someone is asking you to design a robot, like suppose if the payload is less, you don't have to go for complicated model. You can just work with this simple kinematic model, and then you will be able to make the robot work, or you will be able to make the robot autonomous. Okay, and I think I have some more basic terminologies I will explain, and then I'll go to the design of a robot. That also I have included in the presentation. So see, after knowing the kinematics and dynamics, what generally you do is you do the trajectory planning. Trajectory planning means the task description. That means given the task description, a path will be given or a trajectory will be given to you, and that is to be maybe sometimes you may have to find the path. Sometimes the path will be given to you. Okay, so once the trajectory planning is done, so that's the first step. Okay, after kinematics and dynamics, you need to plan a trajectory, and once the trajectory is planned, because planning trajectory is important, because there will be some constraints because of the kinematics, the dynamics. There will be some path constraints, and because of that, the path generated will be different for different robots. So that is why trajectory planning is important. So once the trajectory is planned, then what we will do is we have, see, this is the path to be followed, and how to control the robot in such a way that this follows a particular path. Okay, so that's the next step. So that we call as, this is a see, this particular path is shown, and the robot is made to follow this through this path. So this is done with this reference path is available, or this trajectory is available, and we'll design a controller so that this is move through this path. So this is another scenario. So this is actually robotic manipulator path planning. And this one is what is illustrated is a mobile robot path planning and tracking. See here, no, if you look at this, the robot is following through this particular path. So depending on the scenario, the path will be different. So if there are many obstacles, no, see, this is actually an office-like environment where the robot has to find a path and then it has to follow that. That following path is done by what is called the control. Okay. So once this trajectory is planned, the problem of issuing commands to the joint actuators that will cause the manipulator to faithfully track or follow the planned trajectory is called the robot control problem. Okay, so that means suppose the robot has to follow this path. Then if that is to be done, okay, what is trajectory planning? Trajectory planning means I have theta1t, theta2t, theta3t. Okay, so finding theta1t, theta, the joint angles. Suppose there are 3 joints, theta 3t. So this is called trajectory planning. First step. Okay, so once I know that, then how to track that? Okay, so if the end effector has to be at this point, what should be theta1, theta2, theta3? So the control commands are to be given such that this is the particular theta1, theta2, theta3. Then I move this theta1, theta2, theta3. So I will have some controller, some code which will make sure that at each and every point of time, the specific angles are achieved. So for achieving that, what we are doing, that is referred to as the robot control. Okay. And so this is a typical control schematic wherein we have the manipulator and see, this is the reference trajectory. Okay. And from the feedbacks, see the controller will be issuing commands to the manipulator and the joint angles and velocities fed back. And based on the error, the error, based on the error, the controller will be issuing commands to the manipulator so that it is able to track a particular path. Okay, so this is the last part. So once the initial, all these tasks are done, once the control is also completed, the robot will be able to follow the desired path or will be able to accomplish the task. So see, another scenario wherein a mobile robot is, suppose you have a mobile robot, you will have a typical X reference and Y reference. For example, like suppose the robot has to follow a circular trajectory like this. XR and YR I need to give as, suppose if you give sine t and cos t as the reference, you will get a circular trajectory like this. You will be able to find that. And then you will have a controller and see the controller will be issuing commands to the robot. So what can be control commands? This is left wheel and right wheel velocities. So like designing a controller means, can you find these? Okay, so once you do that, the robot can be made autonomous. Okay. So based on the application, you can rely on the kinematic model, simple kinematic model, or if the payload is more, you can go for a dynamic model. Okay. And if you are a beginner, you can just start with simple linear controllers and all. And once you work, suppose if you feel that the performance of linear controllers are not good, you can go for non-linear controllers. So what generally we do is, if you wish to work in robotics, generally you will be able to do any part of this. You can go for mechanical design, you can do the analysis part, you can do the controller, you can do the control, or you can do the controller design, then you can sensor integration can be done, and you can also implement intelligent algorithms like AI based algorithms instead of this. See, here I have written controller, so that doesn't mean that it's just a PID controller or PI controller. So it can be an intelligent controller also. So if your background is computer science, no, what you can do is you can think of algorithms, AI based algorithms, which are capable of making or achieving the desired task. So ultimately, that is what we have to do, right? So in the first part, I wish to cover only up to this. If you have any quick questions, I am ready to answer. I think it's almost time, right? I have one more design presentation. If you have any quick doubts, I can answer and then go to that. Any quick questions? Okay, can I move on or I need to conclude? See, I have one more presentation because no, there will be some students who wish to start working with robots. So I have just taken a design example. So do I have to explain this or shall I conclude?
Ma'am, you can continue.
Okay, maybe I'll just try to conclude in 5-7 minutes. So this is actually like how you can start working with a design and development of a robot. Okay, so it can be any robot. So what I have taken up to present before you is a design and development of a mobile manipulator. Mobile manipulator means it has a mobile base. Okay, so it has a base and a manipulator. So we call this as a mobile manipulator. So it's not very simple like a mobile base and a manipulator alone. So it combines both. So how can you start with that? It all depends on the application. Okay, so like it all see, for the particular task you are assigned to complete. If this is demanded, then you should go for this. The main attraction of this mobile manipulator is that it has extended workspace. So if you have a fixed manipulator, only particular area you will be able to do the pick and place task. So if a base is moving, means it has extended workspace, right? So if the situation demands, you can go for this. So suppose if this is the task, how to start with? So what you are supposed to do is, whenever you are asked to design a robot, then first do the mechanical design. So it's all, suppose if you wish to work in robotics, it is better to have an interdisciplinary team, so that like there will be contributions from all of them. So the first part is mechanical design, and then comes the electrical and electronic design, then comes the control part, then the testing, and then final the hardware implementation. So how can you start with the system design, the mechanical design? So you need to decide like whether, so there should be a mobile base, whether I should go for a 3-wheeled or a 4-wheel configuration. So maybe as a beginner, what we'll do is we'll just think of a 4-wheeled or 3-wheel configuration, which are in which only 2 wheels are driven and the other 2 are just supporting. Okay, and then what should be the arm? The arm can be very simple. It's not just PPP. Let us go for RPP. Okay, so it's the cylindrical work envelope. So RPP means cylindrical. So that kind of a configuration is assumed, and it's proceeded. And then how we can do the mechanical design. So for that there are so many components associated with this. All these design can be done in SolidWorks. So you can just start working in SolidWorks and design all these components, see all these components and see the dimensions also. And then all these are integrated, and then you need to just start testing that. And then you should have an idea, okay, what should be the base dimension? what should be the wheel dimension, how much payload the robot can take, what should be the speed of the robot, and what should be the speed with load. All these things should be in your mind when you are designing. Then only you will be able to choose the motor. Okay, and then no, you have the link. So first one is the base, then you have the link. So what should be the link dimensions, and what should be the speed of the manipulator, with and without load. And this I'm not explaining because no, it will take time. And then the materials to be chosen for hardware implementation, whether I should go for this aluminum chases or 3D printed chases, whichever, because no, payload is more means 3D printing models, you won't be able to do that. And all these things you need to work with. And then no, comes the first part is over. So you have designed the basic model in SolidWorks, the mechanical modeling is complete. Now comes the task of an electrical and electronic engineer. He or she has to find, what should be the which is a motor. Okay, what should be the torque of that, how to start work. So I'll just explain with an example. Suppose the payload is 4 kg and the diameter of the wheel is 12 centimeter, then so that radius will be just 0.06, and total weight of the mobile base is 6 kg. So you can find the gravitational force as weight into g. So 6 kg into 9.8. So this is the total, but no, the robot is actually there are 2 motors. So that will be divided. The load should be divided among 2 motors. So you can divide that by 2. So it should be able to take this much Newton meter. So adinadutha available aayittulla edu motor aanu ningalku whichever is available, that you can choose. So that is how you go and design or choose the motor. Okay, and then no, you need to calculate the torque requirements of the arm, because this is a mobile manipulator. And then you need to decide which all sensors I need. Okay, only position sensors or velocity sensors, or I need to do some obstacle avoidance. So then which sensor I go for? If I have money, I can go for laser rangefinder. Otherwise, no, okay, budget is less, no, we go for sonar sensors like that. Then we need to decide how the control is to be done. I'm not explaining the details of that, no. So if you we decided to work with the mobile manipulator. So that means the base has to be controlled first, and then after reaching a destination point, the manipulator can be controlled. Okay, simultaneously controlling, as a beginner, no, simultaneous control of base and manipulator will be difficult. Okay, so you will be able to do that if they are done one after the other. The sequential control is preferred if you are a beginner. And then no, like if you wish, no, you can think of implementing advanced controllers like computer torque control, which is a very famous control technique in robotics. I am not explaining that. You can just think of a PID controller, a proportional integral derivative control, which is a very famous controller. So independently, you will be able to control them. Okay. And see, this is a typical block schematic of control of the robot. Okay, so if you have to do this control, no, initially you need to do the modeling, and then only you will be able to work with this controller. And this also, if the payload is 6 kg means, no, you can't work with a very simple kinematic based model. You need to go for a dynamic model itself. So that is why the robot input is a torque. So then only you will be able to work with this model. And see, this is actually the simulation in SolidWorks, which this is actually taken up as some mini project of some of my master students. So this is just a simulation in SolidWorks, how it works. So suppose what I wish to convey to you is that if you wish to think of designing a robot from scratch, it's better to do these steps. So initially do the mechanical design, because no, you should have a plan. What is it? So initially do a sketch and then draw all these components in SolidWorks, integrate them and get the final model. And then you decide which are the electrical actuators or electronic sensors which are being used, which are needed for the application. And then no, see that part I have not included as separately as a slide. Now, the ROS, which is called Robot Operating System, is a very good platform for doing the preliminary simulation analysis of this. So for that, no, what you have to do is the SolidWorks model. From the SolidWorks model, this URDF is to be generated. So the Universal Robotic Description format is generated, which can be imported into ROS, and then no simulations can be done. So, which is a very accepted software in robotics area. Okay, so because no, instead of doing the hardware, if you are working with ROS, that is also acceptable. It's like that. And then no, you need to do the trajectory planning. And then once the trajectory is planned, no, the control is to be done. So here it is mobile manipulator. So that's why it's written as mobile manipulator. It can be a quadcopter. Okay, it can be a humanoid robot. It can be a manipulator, or it can be a pond cleaning robot, or it can be an underwater robot. Okay, so whichever is the robot you are going to work with, these all steps works. And then no, like after testing the simple algorithms like PID control, then you can think of maybe intelligent control algorithms, maybe machine learning based control, or reinforcement based learning control. All those things can be tested. And no, like if you are not interested in doing the simulations, then directly you can go for hardware implementation, because no, if you are simulating in ROS, means hardware integration is quite easier. So whichever be the robot you wish to work with, no, if you are able to follow the steps, ultimately, no, you will be able to happy. Whatever was the objective, you will be able to accomplish that by the end of this project. So that's all I wish to convey to all of you. If you have any quick doubts, I'm ready to answer.
That was a wonderful session. Thank you, ma'am, for sharing your knowledge and experience with us. But before we get into the Q&A, let's take a virtual photograph to capture this moment. So I would like to request you all to turn on your cameras and bring a beautiful smile to your face. And I invite Tinos to do the honor of clicking the picture for us.
So let's please turn on your cameras. So I think we can take the picture. Okay, everyone smile please. Okay, thank you.
Thank you all. A feedback form will be shared in the chat box after the vote of thanks. The certificate will be distributed based on it, so kindly remember to fill it out. Now, let's move on to the Q&A session. If you have any queries regarding the topic, or if you have anything in general to ask the speaker, do feel free to unmute yourself and ask the question. You may also put your queries in the chat box. Any queries? Okay, I think we can move on. I hope everything is clear to you and no one has any questions in your mind. Now, as a token of appreciation from our side, we would like to represent Dr. Jisha V R with a virtual memento. For that, I would like to invite Mr. Tinos Thomas to share the screen and present the virtual memento. Now let's move on to the vote of thanks. Someone has raised their hand. Any questions?
Yes, you wish to ask something?
Hello.
Yes, you can.
Okay, now let's move on to the vote of thanks. For that, let's welcome Ms. Sharanya VS, Web Activities Chair, IEEE Education Society, Kerala Chapter.
On behalf of IEEE Education Society Kerala chapter, I would like to express our sincere gratitude to Dr. Jisha V R for an insightful and engaging presentation on a walk through robotics technologies. Her presentation was truly engaging and made robotics interesting and approachable for all. Her clear explanations, real world examples, and the passion for the subject helped us gain a deeper understanding of robotics, current advancements, and future potential. Her passion for the robotics industry and her dedication to knowledge sharing were truly inspiring. The knowledge gained from this session will benefit all the attendees, encouraging them to ask further questions and pursue their technical and professional interests. We would also like to thank all of you, the attendees, for joining us for this third episode of ProTalks. Your participations and questions are what make these sessions truly valuable. Once again, a big thank you to Dr. Jisha V R for taking the time to share her expertise with us. We look forward to see you all at the next ProTalk session. Thank you.
Okay, thank you, Jisha. The session was very, very informative and very interesting. I hope that everybody എന്താ പറയുക റോബോട്ടിക്സ് എന്ന് കേട്ടാൽ തന്നെ എല്ലാവർക്കും ഒരു നന്നായിട്ടൊരു സ്റ്റാർട്ടിങ് മുതലേ എല്ലാ എഞ്ചിനീയേഴ്സിനും ഏത് എഞ്ചിനീയറിംഗ് ബാക്ക്ഗ്രൗണ്ട് എല്ലാം ജിഷ വളരെ വ്യക്തമായിട്ട് ക്ലാരിഫൈ ചെയ്തും പറഞ്ഞു. എനിക്ക് വളരെ മോട്ടിവേറ്റഡ് ആയിട്ട് വളരെ പ്രസന്റേഷൻ നന്നായി തന്നെ തോന്നി. എനിക്ക് തന്നെ ഒരു ഇൻട്രസ്റ്റിംഗ് ആയിട്ട് തോന്നിയിട്ടുണ്ട്. പക്ഷെ വെരി വെരി നൈസ്ലി പ്രസന്റഡ് ആൻഡ് ഫ്രം ദ സ്റ്റാർട്ടിങ് ടു ദ അപ് ടു ദ ഡിസൈൻ ലെവൽ ഓൾസോ യു ഗോ യു വെൻ വെരി വെൽ. താങ്ക് യു ജിഷ. ഓക്കെ.
With that, we have come to the end of our session. Hope you all had a great time. Don't
There's a question in the chat box.
Yeah.
Anjali, can you read it?
Yes.
Sorry for the late respond. I had a question in mind. Which are the niche domains that requires the need of robotics implementation but haven't been implemented yet?
Having been implemented it, see, you can just think of robots which are trying to help see us, our friends, our parents. Just think of robots which are trying to help your mother in cooking. Because even though there are some robots, cooking robots which are available, it has not yet, that is because of the budget constraints, it has not reached the markets, right? So, and definitely robots which are capable of plucking coconuts. So there are challenges actually. There are some, I think some people have worked with that, but the main challenge in see, I am just talking in the perspective of Kerala, because coconut plucking and all, we may need robots in future. Nowadays, we are seeking the help of Bengalis, right? So the main challenge there is the coconut tree dimension is different, right? But if you take aracanut plucking robots are easier to make because it has some uniform structure. But if you think of coconut trees, it is unique. The design wise, it is If you take different coconut trees, they are different. So can you think of designing that? And there'll be a lot of market. And ഞാൻ എപ്പോഴും വിചാരിച്ചിട്ടുള്ള ഒരു കാര്യം, ഇറ്റ്സ് ലൈക്ക് മൺവെട്ടി. ഓക്കെ, മൺവെട്ടിക്ക് ടാസ്ക് ചെയ്യുന്ന ഒരു, can we have some robots? No, if you think of building those kinds of robot, there will be you will be able to find market for those scenarios. And having been implemented, I'm not see what the examples which I mentioned is not like having been implemented. People have tried that, some of them, but no, like they are not cost effective. So see, suppose if you think of a cooking assistant robot, no, like nowadays people have started buying cleaning robots. So in that way we should be able to buy them. So there are many areas where people will be able to contribute, like the robots which are capable of helping us in day-to-day activities.
Thank you, ma'am. Any more questions?
Dr. Jisha, I feel that there may come a time when robots are simply needed for a companionship. People may become even very lonely, just like the movie.
Elderly companion, that is also, it's there. See, but no, like it should come like a cleaning robot.
Yeah, correct. No, I was just thinking about the Android Kunyappan movie,
Okay.
where a simple companionship may also be needed for people of Kerala in a later stage.
Yes.
Nowadays,
Thank you so much. Thank you so much.
it's also good.
With that, we have come to the end of our session. I hope you all had a great time. Don't forget to fill out the feedback form which is posted in the chat box to get your certificates. Once again, thank you all for actively participating in this event and making it a great success. We look forward to seeing you in our future sessions. Thank you, ma'am. Thank you all.
Thank you.
Okay, thank you.